In mathematics, infinitesimals are things so small that there is no way to measure them. The insight with exploiting infinitesimals was that entities could still retain certain specific properties, such as angle or slope, even though these entities were quantitatively small. The word infinitesimal comes from a 17th-century modern Latin coinage infinitesimus, which originally referred to the infinite item in a sequence. It was originally introduced around 1670 by either Nikolaus Mercator or Gottfried Wilhelm Leibniz. Infinitesimals are a basic ingredient in the procedures of infinitesimal calculus as developed by Leibniz, including the law of continuity and the transcendental law of homogeneity. In common speech, an infinitesimal object is an object that is smaller than any feasible measurement, but not zero in size, or so small that it cannot be distinguished from zero by any available means. Hence, when used as an adjective, infinitesimal means extremely small. To give it a meaning, it usually must be compared to another infinitesimal object in the same context. Infinitely many infinitesimals are summed to produce an integral. Archimedes used what eventually came to be known as the method of indivisibles in his work The Method of Mechanical Theorems to find areas of regions and volumes of solids. In his formal published treatises, Archimedes solved the same problem using the method of exhaustion. The 15th century saw the work of Nicholas of Cusa, further developed in the 17th century by Johannes Kepler, in particular calculation of area of a circle by representing the latter as an infinite-sided polygon. Simon Stevens' work on decimal representation of all numbers in the 16th century prepared the ground for the real continuum. Bonaventura Cavalieri's method of indivisibles led to an extension of the results of the classical authors. The method of indivisibles related to geometrical figures as being composed of entities of codimension 1. John Wallace's infinitesimals differed from indivisibles in that he would decompose geometrical figures into infinitely thin building blocks of the same dimension as the figure, preparing the ground for general methods of the integral calculus. He exploited an infinitesimal denoted 1 infinity in area calculations. The use of infinitesimals by Leibniz relied upon heuristic principles, such as the law of continuity. What succeeds for the finite numbers succeeds also for the infinite numbers and vice versa, and the transcendental law of homogeneity that specifies procedures for replacing expressions involving inassignable quantities by expressions involving only assignable ones. The 18th century saw routine use of infinitesimals by mathematicians such as Leonhard Euler and Joseph Louis Lagrange. Augustin Louis Cauchy exploited infinitesimals both in defining continuity in his cause d'analyse, and in defining an early form of a Dirac delta function. As Cantor and Dedekind were developing more abstract versions of Stevens' continuum, Paul Dubois-Raymond wrote a series of papers on infinitesimal enriched continua based on growth rates of functions. Dubois-Raymond's work inspired both Emil Borel and Thoralf Skolem. Borel explicitly linked Dubois-Raymond's work to Cauchy's work on rates of growth of infinitesimals. Skolem developed the first non-standard models of arithmetic in 1934. A mathematical implementation of both the law of continuity and infinitesimals was achieved by Abraham Robinson in 1961, who developed non-standard analysis based on earlier work by Edwin Hewitt in 1948 and Jerzy Los in 1955. The hyperreals implement an infinitesimal enriched continuum, and the transfer principle implements Leibniz's law of continuity. The standard part function implements Fermat's adequality. Vladimir Arnold wrote in 1990, "Nowadays, when teaching analysis, it is not very popular to talk about infinitesimal quantities. Consequently, present-day students are not fully in command of this language. Nevertheless, it is still necessary to have command of it. History of the infinitesimal. The notion of infinitely small quantities was discussed by the Eleatic school. The Greek mathematician Archimedes, in the method of mechanical theorems, was the first to propose a logically rigorous definition of infinitesimals. His Archimedean property defines a number x as infinite if it satisfies the conditions x greater than 1, x greater than 1 plus 1, x greater than 1 plus 1 plus 1, and infinitesimal if x0 and a similar set of conditions holds for x and the reciprocals of the positive integers. A number system is said to be Archimedean if it contains no infinite or infinitesimal members. The Indian mathematician Bhaskara too described a geometric technique for expressing the change in terms of times a change in. The English mathematician John Wallis introduced the expression 1, infinity in his 1655 book Treatise on the Conic Sections. The symbol, which denotes the reciprocal, or inverse, of infinity, is the symbolic representation of the mathematical concept of an infinitesimal. In his treatise on the conic sections, Wallis also discusses the concept of a relationship between the symbolic representation of infinitesimal 1, infinity, that he introduced and the concept of infinity for which he introduced the symbol infinity. The concept suggests a thought experiment of adding an infinite number of parallelograms of infinitesimal width to form a finite area. This concept was the predecessor to the modern method of integration used in integral calculus. The conceptual origins of the concept of the infinitesimal 1, infinity, can be traced as far back as the Greek philosopher Zeno of Ella, whose Zeno's dichotomy paradox was the first mathematical concept to consider the relationship between a finite interval and an interval approaching that of an infinitesimal-sized interval. Infinitesimals were the subject of political and religious controversies in 17th-century Europe, including a ban on infinitesimals issued by clerics in Rome in 1632. Prior to the invention of calculus, mathematicians were able to calculate tangent lines using Pierre de Fermat's method of adequality and René Descartes' method of normals. There is debate among scholars as to whether the method was infinitesimal or algebraic in nature. When Newton and Leibniz invented the calculus, they made use of infinitesimals, Newton's fluxions and Leibniz' differential. The use of infinitesimals was attacked as incorrect by Bishop Berkeley in his work The Analyst. Mathematicians, scientists, and engineers continued to use infinitesimals to produce correct results. In the second half of the 19th century, the calculus was reformulated by Augustin Louis Cauchy, Bernard Bolzano, Carl Weierstrass, Cantor, Dedekind, and others using the definition of limit in set theory. While the followers of Cantor, Dedekind, and Weierstrass sought to rid analysis of infinitesimals, and their philosophical allies like Bertrand Russell and Rudolf Carnap declared that infinitesimals are pseudo-concepts. Hermann Cohen and his Marburg school of Neo-Kantianism sought to develop a working logic of infinitesimals. The mathematical study of systems containing infinitesimals continued through the work of Levi Civita, Giuseppe Veronese, Paul Dubois-Raymond, and others, throughout the late 19th and the 20th centuries, as documented by Philip Ehrlich. In the 20th century, it was found that infinitesimals could serve as a basis for calculus and analysis, see hyperreal number, first-order properties. In extending the real numbers to include infinite and infinitesimal quantities, one typically wishes to be as conservative as possible by not changing any of their elementary properties. This guarantees that as many familiar results as possible are still available. Typically, elementary means that there is no quantification over sets, but only over elements. This limitation allows statements of the form for any number x, for example, the axiom that states for any number x, x plus 0 equals x would still apply. The same is true for quantification over several numbers, e.g., for any numbers x and y, xy equals yx. However, statements of the form, for any set S of numbers, may not carry over. Logic with this limitation on quantification is referred to as first-order logic. The resulting extended number system cannot agree with the rails on all properties that can be expressed by quantification over sets, because the goal is to construct a non-Archimedean system, and the Archimedean principle can be expressed by quantification over sets. One can conservatively extend any theory including rails, including set theory, to include infinitesimals, just by adding a countably infinite list of axioms that assert that a number is smaller than 1/2, 1/3, 1/4, and so on. Similarly, the completeness property cannot be expected to carry over, because the rails are the unique complete ordered field up to isomorphism. We can distinguish three levels at which a non-Archimedean number system could have first-order properties compatible with those of the rails. An ordered field obeys all the usual axioms of the real number system that can be stated in first-order logic. For example, the commutativity axiom x plus y equals y plus x holds. A real closed field has all the first-order properties of the real number system, regardless of whether they are usually taken as axiomatic. For statements involving the basic ordered field relations plus, times, and, this is a stronger condition than obeying the ordered field axioms. More specifically, one includes additional first-order properties, such as the existence of a root for every odd-degree polynomial. For example, every number must have a cube root. The system could have all the first-order properties of the real number system for statements involving any relations. For example, there would have to be a sign function that is well-defined for infinite inputs. The same is true for every real function. Systems in Category 1, at the weak end of the spectrum, are relatively easy to construct, but do not allow a full treatment of classical analysis using infinitesimals in the spirit of Newton and Leibniz. For example, the transcendental functions are defined in terms of infinite limiting processes, and therefore there is typically no way to define them in first-order logic. Increasing the analytic strength of the system by passing to categories 2 and 3, we find that the flavor of the treatment tends to become less constructive, and it becomes more difficult to say anything concrete about the hierarchical structure of infinities and infinitesimals. Number systems that include infinitesimals. Formal series Laurent series. An example from Category 1 above is the field of Laurent series with a finite number of negative power terms. For example, the Laurent series consisting only of the constant term 1 is identified with the real number 1, and the series with only the linear term x is thought of as the simplest infinitesimal, from which the other infinitesimals are constructed. Dictionary ordering is used, which is equivalent to considering higher powers of x as negligible compared to lower powers. David O. Tall refers to this system as the super-rails, not to be confused with the super-real number system of Dales and Wooden. Since a Taylor series evaluated with a Laurent series as its argument is still a Laurent series, the system can be used to do calculus on transcendental functions if they are analytic. These infinitesimals have different first-order properties than the rails because, for example, the basic infinitesimal x does not have a square root. The Levi-Civita field. The Levi-Civita field is similar to the Laurent series but is algebraically closed. For example, the basic infinitesimal x has a square root. This field is rich enough to allow a significant amount of analysis to be done, but its elements can still be represented on a computer in the same sense that real numbers can be represented in floating-point transseries. The field of transseries is larger than the Levi-Civita field. An example of a transseries is where for purposes of ordering x is considered infinite. Surreal numbers. Conway's surreal numbers fall into Category 2. They are a system designed to be as rich as possible in different sizes of numbers, but not necessarily for convenience in doing analysis. Certain transcendental functions can be carried over to the surreals, including logarithms and exponentials, but most, e.g., the sine function, cannot. The existence of any particular surreal number, even one that has a direct counterpart in the reals, is not known a priori, and must be proved. Hyperreals. The most widespread technique for handling infinitesimals is the hyperreals, developed by Abraham Robinson in the 1960s. They fall into category 3 above, having been designed that way so all of classical analysis can be carried over from the rails. This property of being able to carry over all relations in a natural way is known as the transfer principle, proved by Jerzy Los in 1955. For example, the transcendental function sin has a natural counterpart sin that takes a hyperreal input and gives a hyperreal output. And similarly, the set of natural numbers has a natural counterpart, which contains both finite and infinite integers. A proposition such as carries over to the hyperreals is superreals. The superreal number system of Dales and Wooden is a generalization of the hyperreals. It is different from the superreal system defined by David Tall. Dual numbers in linear algebra. The dual numbers extend the rails by adjoining one infinitesimal, the new element epsilon, with the property epsilon2 equals 0. Every dual number has the form z equals a plus b epsilon, with a and b being uniquely determined real numbers. One application of dual numbers is automatic differentiation. This application can be generalized to polynomials in n variables, using the exterior algebra of an n-dimensional vector space. Smooth infinitesimal analysis, synthetic differential geometry, or smooth infinitesimal analysis have roots in category theory. This approach departs from the classical logic used in conventional mathematics by denying the general applicability of the law of excluded middle, i.e., not does not have to mean or equals b. A nil square or nilpotent infinitesimal can then be defined. This is a number x where x2 equals 0 is true, but x equals 0 need not be true at the same time. Since the background logic is intuitionistic logic, it is not immediately clear how to classify this system with regard to classes 1, 2, and 3. Intuitionistic analogues of these classes would have to be developed first. Infinitesimal delta functions. Cauchy used an infinitesimal to write down a unit impulse. Infinitely tall and narrow Dirac-type delta functions satisfying in a number of articles in 1827, see Lafitz. Cauchy defined an infinitesimal in 1821 in terms of a sequence tending to 0. Namely, such a null sequence becomes an infinitesimal in Cauchy's and Lazare-Carnot's terminology. Modern set-theoretic approaches allow one to define infinitesimals via the ultra-power construction, where a null sequence becomes an infinitesimal in the sense of an equivalence class modulo a relation defined in terms of a suitable ultra-filter. The article by Yamashita contains a bibliography on modern Dirac delta functions in the context of an infinitesimal enriched continuum provided by the hyperreals. Logical properties. The method of constructing infinitesimals of the kind used in non-standard analysis depends on the model and which collection of axioms are used. We consider here systems where infinitesimals can be shown to exist. In 1936, Maltsev proved the compactness theorem. This theorem is fundamental for the existence of infinitesimals as it proves that it is possible to formalize them. A consequence of this theorem is that if there is a number system in which it is true that for any positive integer and there is a positive number x, such that 0 less than x less than 1, n, then there exists an extension of that number system in which it is true that there exists a positive number x such that for any positive integer n, we have 0 less than x less than 1, n. The possibility to switch for any, and there exists, is crucial. The first statement is true in the real numbers as given in ZFC set theory. for any positive integer n. It is possible to find a real number between 1, n and 0, but this real number depends on n. Here, one chooses n first, then one finds the corresponding x. In the second expression, the statement says that there is an x chosen first, which is between 0 and 1, n for any n. In this case x is infinitesimal. This is not true in the real numbers given by ZFC. Nonetheless, the theorem proves that there is a model in which this is true. The question is, what is this model? What are its properties? Is there only one such model? There are in fact many ways to construct such a one-dimensional linearly ordered set of numbers, but fundamentally, there are two different approaches. 1. Extend the number system so that it contains more numbers than the real numbers. 2. Extend the axioms so that the distinction between the infinitesimals and non-infinitesimals can be made in the real numbers themselves. In 1960, Abraham Robinson provided an answer following the first approach. The extended set is called the hyperreals and contains numbers less in absolute value than any positive real number. The method may be considered relatively complex, but it does prove that infinitesimals exist in the universe of ZFC set theory. The real numbers are called standard numbers and the new non-real hyperreals are called non-standard. In 1977, Edward Nelson provided an answer following the second approach. The extended axioms are IST, which stands either for internal set theory or for the initials of the three extra axioms: idealization, standardization, transfer. In this system we consider that the language is extended in such a way that we can express facts about infinitesimals. The real numbers are either standard or non-standard. An infinitesimal is a non-standard real number that is less, in absolute value, than any positive standard real number. In 2006, Carol Hrbacek developed an extension of Nelson's approach in which the real numbers are stratified in many levels, i.e., in the coarsest level there are no infinitesimals nor unlimited numbers. Infinitesimals are in a finer level and there are also infinitesimals with respect to this new level, and so on.